Alright, this lesson we're looking at using data transformation. So to understand data transformation, you need to make sure you understand a couple of concepts from our previous topics. So go back to these notes if you feel like you need a little bit of reminder. But I'll go over it very briefly. So we looked at the R squared value, which tells us how much of our association can be explained by the R value, whether if there's other factors that were affecting the association. So higher the R2 value, the better. And then we also looked at using the residual plot to determine whether we can assume there's a linear association between two variables, and we wanted our residual plot to look random like this along the x-axis. We didn't want any patterns in our residual plots, and if that was the case, then we can't assume that the association is linear. So knowing these two and knowing what shape that our scatter plots will take between our x and y variables, here are the lists of data transformation that we can perform. So this one hasn't been covered, so if this looks new to you, you're not doing anything wrong. This is later on to sort of summarize everything. Today we're looking at just the first couple, which will be to do with square transformation. So we're looking at graphs where it has a pattern. So when we draw the scatter plot, you could sort of see that it's linear, but if we're really careful, then it's not actually linear, it's more like a curve. Or we could get a pattern that's going on this curve. So this first curve, x squared transformation, would help us linearize the data, so make it more of a straight line rather than a curve. And for the second curve, if it looks like this, then a y squared transformation, so squaring the y, will help us linearize the data, so making it more linear. So let's look at some examples. So this first example here, we have a whole bunch of data, and as you can see, they're just x and y at this point. And when we plot this data on a scatter plot for x and y, you can see this isn't a linear relationship, this is more like a curve. And then just to confirm that it is not linear, we can plot a residual plot, really important, and hopefully it has a pattern that is as obvious as this one. Then we can be for sure that this is not a linear association between x and y. And then when we did the R squared value, it's very high. It's at 92%. And then when we use the CAS to find the line of the regression, the least squares regression line, we have an equation that looks like this. Now, just because we can get a linear equation and an R squared value that's high, doesn't mean that we can assume this is a linear relationship. If we look at the residual plot, we know there's a clear pattern, so we know that this isn't a linear relationship. So if we're asked to comment on the suitability of using this as a linear model, we can say it's not suitable because of the following reasons. So the presence of the clear pattern in the residual plot, and so x and y is not linear. However, this is something that we can fix. There's a clear pattern here. So if we square this x, so the x that was used here, or also over here, if we square these values, so we're just essentially just squaring all of these values. So this will become 1, this will become 4, this will become 9, this will become 16, so on and so on. If we do that, then that's going to help us linearize the data. And the reason why we're squaring the x, not y, it's because it's following this pattern where we should square the x to linearize the data. So we simply introduce a new row of data where all the values of x are just now squared. And then if we plot it again, then we'll have a more straight line, which is what we like to see. And then if we, using this squared line, if we find the equation of this line, which we can do using the cas, only thing you need to be super careful of is now we're not using x anymore, we're using x squared, so we're going to have x squared where our x used to be. And then when we find the r squared value, also using the cas, now we can see it's almost at 100%, which is amazing compared to our original, which was still high at 93, but the new r squared value is higher. So this is definitely better, and we can see the lines more, the scatter plot's more linear as well. So this was a good suitable transformation for this data. So once we transform the data, make it more linear, then we can use the equation, the new equation, one with the x squared, to make predictions. So we can make predictions like find the y value when x is 4.5. All you have to do is replace x with 4.5. Make sure to square that as well, because now we're doing x squared, so we can do that for any value. Obviously we can do it for 8 here as well.